To build a computer or process basic information, you have to be able to control the direction and flow of electrical charge. For decades, the electronics industry relied entirely on vacuum tubes to do this. These bulky glass bulbs had to boil electrons off a heated metal filament called a cathode. They consumed enormous amounts of power, generated intense heat, and shattered easily. Engineers referred to them as valves. Because they operated in an evacuated vacuum space, the charged electrons could only travel in one direction, from the heated cathode to a positively charged metal plate. In the 1930s and 40s, researchers discovered they could eliminate the vacuum and the extreme heat. They found a way to control the flow of charge carriers directly inside solid, room-temperature crystals. This realization eventually killed off the old cathode ray tube display, or CRT. A cathode ray tube is a deep, heavy vacuum funnel that shoots a beam of electrons at a phosphorescent screen to create an image. The semiconductor diode successfully shrunk those massive, fragile valves into microscopic components that required no physical space and minimal power. A modern semiconductor diode operates as a strict one-way street for electricity. It lets current flow freely in a single designated direction while blocking it from moving in reverse. We use them to convert alternating current, which reverses direction back and forth, into steady direct current. This steady power is required for modern liquid crystal displays, or LCDs, screens that use liquid crystals and light filters to produce digital images. But without any moving parts or heated filaments, how does a tiny solid piece of silicon actually block current in one direction while letting it surge in the other? The mechanics rely on a microscopic boundary called a p-n junction. A p-n junction is created by taking a single semiconductor crystal and doping it, adding impurities to change its electrical properties. One side is packed with extra positive charge carriers called holes, while the other side is packed with negative electrons. To wire this crystal into a circuit, manufacturers attach metallic contacts to the far edges of both the p side and the n side. In an electrical schematic, this component is represented by a standardized symbol, a triangle pressed flush against a vertical line. The flat vertical edge of that triangle acts like an arrowhead. It points in the direction that conventional current is allowed to travel through the wire. While it looks like a simple two-terminal connection, the microscopic border where the two materials meet acts as an invisible, self-regulating gate. The moment you join these two materials, particles move. Because the n side is dense with electrons and the p side is dense with holes, they naturally diffuse across the border toward each other. As electrons migrate over, they leave behind positively charged immobile ions on the n side. The holes leaving the p side leave behind negative ions. This creates a central zone right at the border that is wiped clean of free charge carriers, appropriately named the depletion region. This graph shows the voltage across that junction. The buildup of positive and negative ions creates its own localized electric field, resulting in a step-like curve. This is the barrier potential, and it acts like a steep hill that prevents any more stray charges from wandering across. This internal electric field pushes carriers back as fast as they try to cross. With these forces perfectly balanced, the diode rests in equilibrium, and zero net current flows through the device. That barrier is the physical wall stopping the traffic. To get electricity moving again, an external power source, like a battery, has to either flatten that hill or build it up higher. If you connect the positive terminal of a battery to the p side and the negative terminal to the n side, you apply forward bias. The battery's external voltage opposes the diode's internal electric field. This drops the height of the energy hill and physically narrows the depletion region, allowing a flood of electrons to cross the junction. Current flows freely. But if you flip those battery terminals, connecting the positive end to the n side and the negative end to the p side, you apply reverse bias. Now, the battery's voltage adds directly to the internal barrier potential. The energy hill gets taller, the depletion region widens, and the gap becomes impassable. The flow of current is choked off. To push current through a standard silicon diode in forward bias, your battery only needs to overcome a threshold or cut-in voltage, typically about 0.7 volts. By applying just a tiny external voltage, we can dynamically reshape the atomic landscape of a solid crystal. This simple ability to open and close a microscopic gate is exactly how we direct the flow of information across the digital world.